Sorry about this. My talk will contain much less information than my course. Slower pace. And hopefully you'll know most of it. And maybe you'll find some of it interesting. That's best case scenario. So, story begins about 50 years ago. Erdos and Renyi introduced a couple of models for generating random graphs. We start with n isolated vertices, and in the GNP model, each of the entries to possible edges is present independently with the same probability p. In the GNM models, you specify the exact number of edges that you want, and among all possible subsets of that many edges, you pick one uniformly at random. Perhaps one way to think about these models is if you take the lattice in which at the bottom you have the empty graph on n vertices, and on the top you have the clique on n vertices. The GNM model, you specify exactly where you want to be on the lattice, and it picks a uniform random element. The GNP model puts a little binomial distribution around this, but you have sharp concentration, so it's essentially the same. Of course, moreover, conditional in GNP on the exact number of edges the model produces in GNM. And what is particularly interesting to study in this context is so-called monotone properties. So you can think of this as the characteristic function of your property. It separates the graphs that have the property with the graphs that don't have the property. And then as you increase the number of edges, at some point you go from graphs that typically don't have the property to graphs that typically have the property. And a very interesting question is, how fast is this transition? As you can imagine, the transition is absolutely fastest when the property in question is how many edges do you have. Okay, so here's an example of a property that is very well understood and relatively impressive. So remember that P is the probability of an edge being present. So the average degree is roughly the numerator in this expression. So when the average degree is just below n, if you look at all connected components in the graph, their size is at most logarithmic in the number of vertices, and their structure is very simple. They have at most one cycle. And then you make the average degree go just above 1. And while the rest of the graph stays the same, you actually get a single component that has linear size, that has very complex cycle structure. Is there a question? So the critical probability, therefore, for this property is 1 over n. And if you look at this giant component, it's sort of born rich. It immediately and instantaneously has huge complexity. So what I mean by huge complexity is that it has small diameter. If you take your random walk inside it, it will mix in a polylogarithmic number of steps. If you try to cut it into 2 parts, you can't do a good job, meaning the number of edges you will have to cut is roughly the same that you would cut if you tried to cut it at random. If you look at a vertex, and then you look at its neighbors, and their neighbors, and their neighbors, and their neighbors, for any finite distance you will see a tree. So it's locally tree-like. And one implication of this fact, more or less, is that it behaves like an expander. It's actually a pretty high-quality expander. So this is when the giant component shows up. And sort of these Erdos-Renyi random graph have all sort of other mathematically expedient properties. The degrees of the vertices are essentially independent random variables. In fact, the joint degree distribution behaves like the joint distribution, a product of independent Poissons is like a giant balls and bins experiment. The edges, each edge you can think of as throwing 2 balls inside n bins. That's basically what happens. We know that in balls and bins things Poissonize and everything is super nice. But then you get other sorts of miracles. So if you follow this balls and bins paradigm, I said that you can think of each edge as consisting of 2 balls. Therefore, if I throw in 1/2 n log n edges, it's like I've thrown n log n balls, and this is, if you know the expression for the coupon collector problem, this will be the first moment where everybody has degree 1. Okay? Now, having degree 1 is an absolutely necessary, a trivially necessary condition for the graph to be connected or for the graph to have a perfect matching. Yet in a random graph of this nature, as soon as this trivial condition is satisfied, the graph is connected and has a perfect matching. So in fact, if you play the game as in I add one edge at a time, the edge that will make the graph have this property will be the edge that will make it have these two properties. And effectively what is happening is the rest of the graph is accumulating complexity, and they're just waiting for everybody to hook up. As soon as even the last person hooks it, there's tremendously rich structure inside which you can get things done. And it gets sort of even more impressive. As soon as every vertex has degree 2, the graph has a Hamiltonian cycle. Okay? It's a cycle that allows you to go through every vertex exactly once. A trivial condition for this is having degree 2. You've got to get in and out of each vertex. And in the same spirit, as you add edges one by one, the edge that gives you minimum degree 2 gives you a Hamiltonian cycle. Moreover, the graph is so rich in Hamiltonian cycles that you can find one in linear time, in expected linear time. And interestingly enough, observe that this is n. It's not even n log n, meaning you can find the Hamiltonian cycle without even really reading the entire input. Okay, because there's just such an abundance. Okay, so these things are nice. And this sort of nice symmetric structure of random graphs allows us to get a handle on things that somehow morally it feels like we shouldn't have the right to answer questions like this. Okay? So one way to perhaps think of Erdős-Rényi random graphs is you start with a fat clique, and these are the vertices. Think sort of as the edges as layers. Okay? This is the clique, and then you peel off, you thin the clique until you get to something that has a linear number of edges. But I claim it's still so nicely structurally balanced that you can prove things like this. Can you get the keynote to it? Okay. So, for every constant c greater than 0, with probability that tends to 1 as the number of vertices tends to infinity, the chromatic number of a random graph with n vertices and c times n edges is either k or k plus 1, where k is the smallest integer such that c is less than k plus k. Okay, so remember the chromatic number of a graph is how many colors do you need so that you can color the vertices such that adjacent vertices receive different colors. This is a standard sort of NP-complete problem. So this says, if the number of edges is 6.73 times n, so the average degree is about 13, then with high probability the chromatic number is either 5 or 6. On the other hand, if c is 10 to the 60, then with high probability the chromatic number is either this or this. Okay? And I'm happy to have sort of shown this result. At the same time, I think this result is a bit of an embarrassment to the model. So there's this quantity, the chromatic number of a graph is ridiculously complicated invariant. You have no idea how to find such properties. Yet the model allows you to prove things like this. So maybe this is a bit suspect. So anyhow, the first question I want to ask is, do these Erdős-Rényi random graphs look anything like real graphs? And for this I will give some experimental evidence that it's kind of dated, but I think it's kind of nice to look back a little bit. So this is the MSN Messenger graph, circa 2003. So this is the heyday of Windows XP. XP is pushing MSN Messenger to your face. You almost have no choice. It's kind of funny. I look at the audience, and some people here are young enough to not know what I'm talking about. It's bad. So anyhow, there was a moment when Microsoft was the owner of a social network with 110 million people and 2 billion connections. A year later, Facebook is coming. So most of these links are bidirectional. 110 out of the 112 million vertices form a single connected component. The second largest component has 84 vertices. Okay? And this is kind of nice. This is one thing that really conforms to the theory of Erdős-Rényi random graphs. It more or less says as soon as starting begins to grow, it'll get absorbed. It is sort of very, very unlikely that we won't have any connection to the big guys. But if you look at the joint degree distribution, so this is the number of people sort of that are on your buddy list whose status you're watching, and this is the number of people that are watching you, and this is the logarithm of the number of users with this number of vertices. This is already pretty far off what a random graph as Erdogan would predict.
But then that result sort of, I mean, insofar as Erdogan is good, which maybe I'll get to, it's not, but insofar as it's good, that's saying it's Erdogan and that extremely sparse P regime also.
What is?
That result you just pointed out with 84
previous
vertices
one.
is Erdogan in the extremely sparse value of P regime, right?
Sure, but I mean, what I'm saying is you don't really need much to believe this, right? You don't really need a particular network model. Yes? So this statistic is already off. It's also kind of fun to actually interpret sociologically what the difference in this two plot means about vanity and social isolation. So anyhow, this statistic is off. But perhaps the statistic that is most off is, you can think of it as transitivity of adjacency. If Jack and Jill have a common friend, they're 18,000 times more likely to be friends themselves. The number of triangles is 18,000 times more what Erdős-Rényi would predict. And here are some sort of depth tree neighborhoods. And as you can see, they look nothing like trees. So part of the reason we got our hands on that graph was because our goal was to try to come up with a partition of this graph into parts such that there are few edges between the parts. From a systems point of view, this made a lot of network maintenance operations much more efficient. And ultimately what we came up with as sort of a theory as to the object that we were looking at is that the graph could be thought of as a superposition of two graphs. There are a lot of local edges. Meaning, you could perhaps explain 60% of the edges in the graph just between people going to the same high school. So this gave you a geometry. Nonetheless, there were also sort of, let's call them random-like connections, which were a non-trivial fraction of all edges, maybe something like 10%, which is kind of what happens when people move from high school and end up going to grad school, where people from all over the world show up. And you make connections with people that don't correspond to your original geographic vicinity. So these short hole links cause clustering coefficient being high, meaning that you have a lot of local triangles and dense subgraphs. On the other hand, the presence of long hole links causes what I described earlier as expansion. So we'd like to fix this and come up with models that are more realistic. So perhaps the most obvious thing to try to fix is the degree distribution. And we can start with the simplest world where you look at random regular graphs. So one regular graph, random or not, is just a matching. A two regular graph, again, random or not, is the disjoint union of cycles. It's the only way that everybody can have degree 2, so you have a bunch of cycles. Okay, what about three regular graphs? What about a typical three regular graph? And then, interestingly enough, you get sort of a phase transition in complexity between 2 and 3. And a random three regular graph with high probability, has logarithmic diameter, is a fantastic expander, and it contains a perfect matching in a Hamiltonian cycle. Yes.
So how do you generate it? So what's the model for a random regular graph?
Okay, we will see that in a second, but take all three regular graphs on vertices, put them in a bag, and throw. This is the distribution.
Yeah.
We will later see a very, very nice structural result about this. But it will be helpful in understanding that result to remember this. This is a claim I'm making. Yes? That a random irregular graph contains a perfect matching in a Hamiltonian cycle. And then we will see how this also relates to generation. So my point is, a random irregular graph is already something terrible. Okay? And by terrible, I mean it is a dimensionality monster. It's an incredibly complex object. You cannot embed it in a low-dimensional space and present anything about it. And one nice way to express this fact is that there is a general problem if you take an arbitrary endpoint metric and you would like to embed it so that the original distances are preserved up to a distortion factor. And there's a nice theorem of Wood-Gen that says this is always possible if you're willing to tolerate distortion up to log n. And there's another theorem by London, Gillian, and Rabinovich saying this is best possible. And the theorem that makes this go through is this. Okay? If you take the shortest path metric of a random 3 regular graph, and you try to embed it in any LP norm, not just the worst case, but the average distortion, is what we're getting from the system. Okay? So this is saying if you take a random 3 regular graph, and then you say the distance between every 2 points is the number of hops that you have to travel to go from A to B, and these are the numbers, there's no way you can come up with a point cloud that lives in low dimension, such that the distances between 2 points have a good correlation with the original method. It's sort of incompressible. You cannot put it in the dimension. So I would like to use this fact to sort of show that some other attempts to create random graph models that are more realistic inherit the problems that come from dimensionality, which in turn comes from independence. So one idea to try to get so-called small world graphs is to start with some kind of a low-dimensional lattice, like this one, where you have every vertex connect to all vertices that are within a certain distance, k. Think of k as a small number. And then perhaps you augment this, either by rewiring some of these edges or by just throwing on a few edges at random. And people have sort of argued, well, this is a realistic model, it has this property and that property and so on. But the truth of the matter is, even if I take this and I strip it down to just a circle, and the only edges I add are a matching, what I get is a random 3 regular graph. Okay? And that's a deep theorem. Okay? But one way to generate random 3 regular graphs is take a cycle and throw on a random matching. Okay? That's a highly, highly non-trivial mathematical statement, but it's true. And what it tells you is that any construction along the lines of start with a low-dimensional lattice and augment it will reproduce the monster. Okay? That's the point. So this means that if you wanted to do, let's say, efficient routing on a random 3 regular graphs, yes, there are short paths, the diameter is very small, but the lack of respect for local geometry, in the sense that the graph was generated by adding a random matching to this, means that building the network is going to be expensive because the vast majority of edges are going to have length that is proportional, to the size of the graph. And you will need global knowledge to do the actual routing. Because in a certain sense, the graph could be this one, or it could be that one, or it could be this one, or it could be that one. There is no respect for the underlying geometry with respect to the completion. So you have to remember all that stuff. I really love this. Okay. So let me talk about a couple of efforts. How much time do I have to? How much? 10? Perfect. So we can try to lower the dimensionality. Here's a model that was proposed some time back as a very simple model for internet growth. We think of vertices as uniformly random points on the unit square, and every vertex that arrives has to optimize a trade-off between, if you would like to connect to someone who's already present so that it has connectivity, and on one hand it would like to connect to someone who's close, on the other hand they would like to connect to someone who is central. Okay? And the picture will sort of explain the trade-off. So remember, points are arriving at random, one after the other. Okay? And if copper is very expensive, most vertices will connect to someone nearby. If copper becomes cheap, then the first few arrivals will actually end up sucking most of the noise. Okay? I'm not saying this is a terribly interesting model, but at least to me it highlights the fact that networks typically are created for a purpose. And you can get some theoretical results about what the degree distribution of such a graph is as a function of the price of copper. Another question that I think is very nice is, our graphs might have very nice global properties, but in a certain sense, graphs are experienced locally by the vertices. And what I mean by this is, take a low-dimensional lattice and add one long link per vertex at random, where the distribution of the long edge has a drop-off that is like 1 over the distance to some power. Okay, so you take a low-dimensional lattice, you augment things with a single long-dimensional edge. And what you would like to do is ask the following question. And this, by the way, is a beautiful model that was introduced by Kleinberg about more than 10 years ago. You would like to enable communication by greedy routing. Meaning, if I'm here and I want something somewhere else, I ask myself, does my long link take me that direction? Yes or no? If yes, I take it. Otherwise, I move to one of those two and I ask again. Okay? So there's a sense of gradient in which you either make small steps or occasionally you'll be able to make a large step. And this was motivated largely by Milgram's experiment and the idea of 6 degrees of separation. But if you want to send something to someone, typically there's some information gradient that allows you to move in the right direction, and sometimes you make big jumps. And what Kleinberg proved was something quite nice. He said, well, if r equals 0, then the distance effectively becomes irrelevant. The long link is uniformly distributed over the entire system. On the other hand, if r equals 2, i.e. matching the dimension of the lattice, you get that the long-range destination is at a distance scale from where you are, 2 to the I, uniformly. So with a reasonable chance at distance 1/2, with an equal chance at distance 4, with an equal chance at distance 8, 16, 32. So now if you think about it, this makes sense. You can actually route efficiently in this, because no matter where you want to go, you have a reasonable chance, a 1 over log n chance that you can make the distance be half with every effort. And if you don't make it half, you move to the next neighbor and you get a fresh trial. So this allows greedy routing in a logarithmic number of steps with this very, very carefully crafted probability distribution for this sort of very specific model. So it's a nice proof of concept. There exists a distribution that augments some low-dimensional space that makes it possible to get navigability, meaning not just the existence of short connections, but short connections which are discoverable in this local greedy sense. So what I will talk about next in the last, I guess, 5 minutes is a new model of random graphs, which somehow tries to address that, on one hand, the dimensionality monster, yet at the same time remain mathematically tractable. And the next picture I think is very ugly, but that's the only super ugly picture, so hopefully. So I'd like to do things as general as possible. In particular, I'd like to create a model in which I've separated out the things that we know about the network we're going to work out versus the randomness. So what do I mean by this? I have a collection of vertices, and I have a length function. So for every pair of vertices, there is a notion of distance between them. And the input that the user gives me that. I don't propose any specific method for creating the geometry. That's input to the model. You tell me what is the distance between any pair of points that you like. So this corresponds perhaps to some latent semantics that you have, if it's data, but it could also correspond to, here's a city, here's another city. Okay? This is input. And there is also an arbitrary cost function, which doesn't have to be monotone, and this doesn't have to be a metric, which says, if you want to realize edges of a certain length, these edges have this cost. That's it. And I would like to study graphs which are uniformly random among all the graphs on this cost geometry that respect a certain budget. So a simple way to think about this is, I have a bunch of points on the plane, and I have a spool of copper wire, okay, that has a specific length. Take the set of all possible graphs that can be realized using up to this much wire on these points, put them in a bag, draw one at random. What can you say about it? And remember, I'm not making any assumptions, either on the nature of the points or on the cost function. The cost function doesn't have to be a length, it can be an arbitrary function of the length. So it's, in my opinion, extremely minimal in terms of assumption. The only assumption I'm making is that I would like to study the uniformly random measure of such graphs. Nothing else. Everything else is user provided. Yes?
So I don't get it. How is the edge length? Do you have some constraints that the lengths in your graph you get are close to the?
Remember, I have sort of two layers of abstraction. One is length, but the other one is the cost of realizing an edge of length. So what I am constraining is the sum over all the edges that you're going to actually choose to put in your graph of the cost of realizing them. So each such edge that you choose to put in will have a length.
So the length will be exactly realized in your graph of each edge, or
In the case of copper, f is the identity function, right? In the way we think about it. So if these 2 points have distance 3, I cut a piece of wire that has length 3, yes, and that's what I put in. But it could be that my cost function is not linear. So I just have a budget. And what I'm constrained is that the sum over the edges that I choose to realize of their realization cost, where the realization cost is a function of the distance between the points, between the lengths, is constrained to be no more than some constant time, some number times that, so n is just for scaling. So this is the average budget per vertex. You can think of C as a substitute for the degree. Does this make sense?
no? But I don't get it.
It's less or equal, yes, this should be less or equal. But it turns out the measure is dominated by essentially, because entropy pushes you to use all the wire. Yes?
No, but if it's less or equal, why couldn't you just like have every don't have any edge? Essentially?
Yes, you could. But there is
So
only
what
one
prevents
graph with no edges, and there are tons of graphs with 1,000,000 edges. So inside this bag, there are a lot of graphs that I can realize, and I pick one uniformly. Does that make sense?
Maybe you continue and maybe it makes sense in the end. I'm not sure. But
Yes.
Just to make sure I'm not missing something, why do you need F and L separate? I mean, why not just apply F and L? Because L is not a
Good
measure.
point. Well, if there is time, one thing that I'm interested in studying is you have a specific geometry, but what changes is technology. Okay? So technology can take a cost that used to be linear and drive it to become significantly sublinear. And I would like to be able to study the effect of technology on the graphical structure. And it's nice to have this separation. To sort of, for example, you can say, take the lattice, the three-dimensional lattice, and see what happens as technology changes. Where technology represents the fact that the marginal cost as a function of the length changes over time. That's the only reason. But I think that might have been also the cause for the confusion. You are right. I could do everything if the two things collapsed. Okay? Does that answer your question?
Yeah, just making sure I'm not missing something.
So again, I'll try to say it one last time. I have a collection of points. Between every pair of points, there is a number called the distance between these points, the length of the corresponding edge. And I have a generic function that takes as input the length of an edge and tells me how much it costs to realize that edge. I have a budget, and I'm saying, among all possible graphs that you can realize, by using no more, this should be an inequality of this quantity budget, put them all in a bag, every single graph that is realizable with your budget, put it in a bag, and then draw one at random, and if you can, tell me something about it. Okay? Is the model clear?
But is it the distance or it's just the cost?
What is it?
L.
N is the length or distance.
Is it the shortest path?
No. It's an arbitrary function. You give me, okay, the input to the model is to this. You give me a matrix, yes, a symmetric matrix. Vertex, vertex, number.
The little triangle inequality.
No triangle inequality. It is not a metric. Okay? It is not a metric. So I said it at some point, maybe I said it too fast. This is an arbitrary function. I require symmetry so that the model is undirected, okay? In fact, it could probably handle directed edges as well. But it is not a metric. There are no structural assumptions. Okay? This is not a metric. This is not a monotone function. Okay. So, Obviously, I'm not making any independence assumptions between the edges. I'm not putting in a priori anything. The only thing I'm saying is uniform, subject to being realizable. That's it. Now we've more or less run out of time. Okay, forget the slides. So here I will try to tell you what happens, because in 1 minute you can't do it otherwise. So take one bucket and put in all the edges that have cost of realization, let's say for simplicity between 1 and 2. Then make another bucket, 2 and 3, make another bucket, 3 and 4, and so on. So do some kind of a binning of the costs so that you just have a sublinear number of distinct costs. Okay? What we prove is, if you take a uniformly random graph on this model, what it looks like is, first of all, if you take a graph, there's going to be some edges from this bucket, some edges from this bucket, some edges from this bucket, some edges from this bucket. Yes. The first statement, which is easy, is that conditional on how many edges you take of each length, this subset of edges is uniformly random. That's the easy part. The hard part is, if you look at this vector of how many edges you take from each bucket, this is a sharply concentrated random variable, so it behaves effectively as a deterministic random. And this concentration statement is really not trivial, because we start from nothing. The only thing that we have to extract it from is the uniform number. So this is saying that you can actually get a lot of mathematical control on these graphs, because you can partition your problems by saying, I first have a conditional, I know what will happen. The input distribution will specify how many edges I will take from each bucket, and this is just a solution to an entropy energy optimization problem. Okay? But the difficult part is to say, modulo that, things are concentrated. So to give you some idea, let me just say 2 things. One thing that we get is that this is a natural model in which you get a clustering coefficient. You get local density without having to ask for it yourself. And the reason is, if you look at triangles, okay, remember that the probability that you will see any specific triangle will end up being exponentially small in its perimeter. Because a big triangle has big cost, a small triangle has small cost. Okay? So the triangles that you will see are going to be triangles that are formed by nearby vertices. So just the energy minimization will actually create local structures without you having to do anything about it. Another thing is, you can get control at a level that is sort of, to us it was quite unexpected. So here's the theorem, it quotes. If you have a coherent cost geometry, which I will not define, but it sort of means that you have some kind of information gradient like you had in the grid. In particular, our definition of coherence includes every known model for which navigability has been studied. And you take a uniformly random graph subject to a budget on this cost geometry. This graph will be navigable for the smallest possible value of the total budget for which navigability is possible. Okay? Meaning, if you want to create navigable graphs, the best thing to do is just sit back and watch. You don't have to do anything. Okay? As long as you have a substrate that is coherent, meaning something like a lattice or some kind of hierarchy in which it is possible to have navigability, unlike in an expanded graph, energy optimization alone will make the graph navigable, as if you actually try to engineer navigability in the network. So this is perhaps the first property that we sort of know that is explicitly stated, in which engineering is meaningless. You don't have to do it. Nature can just do it at random. A uniformly random graph that conserves energy, that is the total connectivity cost, will have navigability for free. You don't have to work with it.